mais ou menos, mais ou menos.
E atenção, se liga aí que é hora da revisão.
Não sei. Não sei.
No, God! No, God, please, no! 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 No!
Skeletal muscles are composed of bundles of muscle fibers. Muscle fibers are long cylindrical cells containing several nuclei. Muscles will contract or relax when they receive signals from the nervous system. A neuromuscular junction is the site of the signal exchange. This is where the synaptic bulb of an axon terminal and muscle fiber connect. Muscle fibers are composed of many myofibrils. A myofibril contains contractile units called sarcomeres. Sarcomeres run adjacent to one another down the length of the myofibril. Each sarcomere consists of alternating thick and thin protein filaments, giving skeletal muscle its striated appearance. The muscle contracts when these filaments slide past each other. The thick filaments are myosin, which are anchored at the center of the sarcomere, called the M line. The thin filaments are composed of the protein actin, which are anchored to the Z lines on the outer edges of the sarcomere. Because the actin filaments are anchored to the Z lines, the sarcomere shortens from both sides when actin filaments slide along the myosin filaments. Although the action between the filaments is described as sliding, the myosin filament actually pulls the actin along its length. The cross bridges of the myosin filaments attach to the actin filaments and exert force on them to move. This action is known as the sliding filament mechanism of muscle contraction. In this model, the sarcomeres shorten without the thick or thin filaments changing in length. A contraction begins when a bound ATP is hydrolyzed to ADP and inorganic phosphate. This causes the myosin head to extend and can attach to a binding site on actin, forming a cross bridge. An action called the power stroke is triggered, allowing myosin to pull the actin filament toward the M line, thereby shortening the sarcomere. ADP and inorganic phosphate are released during the power stroke. The myosin remains attached to actin until a new molecule of ATP binds, freeing the myosin to either go through another cycle of binding and more contraction or remain unattached to allow the muscle to relax. Muscle contractions are controlled by the actions of calcium. The thin actin filaments are associated with regulatory proteins called troponin and tropomyosin. When a muscle is relaxed, tropomyosin blocks the cross-bridge binding sites on actin. When calcium ion levels are high enough and ATP is present, calcium ions bind to the troponin, which displaces tropomyosin, exposing the myosin binding sites on actin. This allows myosin to attach to a binding site on actin, forming a cross bridge. Calcium ions are stored in the sarcoplasmic reticulum and are released in response to signals from the nervous system to contract. Neurotransmitter molecules are released from a neuron and bind to receptors, which depolarizes the membrane of the muscle fiber. The electrical impulse travels down the T-tubules and opens calcium stores. Calcium ions flow to the myofibrils, where they trigger a muscle contraction. As the actin and myosin slide along each other, the entire sarcomere shortens as the Z lines draw closer to the M line. As the sarcomeres in myofibrils contract, the entire muscle fiber will shorten.
Microtubules are the tentpoles that give stability and rigidity to your cells. They're made up of a protein called tubulin, which comes in two flavors, alpha and beta. Alpha and beta tubulin bind together in what we call a dimer, and that dimer binds to other dimers until you get a spiral that goes all the way around. It takes 13 dimers, or 26 tubulin proteins, to make one cycle, so for a single microtubule you easily need more than 1,000 individual tubulin proteins. So how are these microtubules made? Well, piece by piece. If one microtubule needs thousands of proteins, that means that every cell must have many copies of both alpha and beta tubulin. Since alpha and beta tubulin only bind to one another in a very specific orientation, they automatically assemble in the right way to form a microtubule that can dynamically extend. Now you'd think these tentpoles would get in the way every time a cell needs to change shape or move somewhere, but fortunately for us, microtubules are dynamic. This means that they're also a touch unstable. Microtubules can start to disassemble in what is known as a catastrophe. After having grown for a bit, they're able to suddenly fall apart and peel off as individual filaments. But that's only part of the microtubule story. Microtubules are also the railroads of a cell. The inside of your cells is made up of a thick salty liquid called the cytosol. Inside it, loads and loads of proteins float around until they happen to arrive wherever it is that they kind of wanted to go to. So what happens when proteins have a very specific place that they want to go to, that they wouldn't easily reach by floating around and randomly bouncing off of other proteins? This is where the microtubules come back in. Because they form a network that goes pretty much anywhere in a cell, and because they're generally quite sturdy, microtubules are the train tracks that you can transport cargo down. Cellular cargo needs a molecular freight train to carry it along the microtubules, and that is a protein called kinesin. Kinesin is able to bind to tubulin with its two feet-like motor domains and slowly work its way up the microtubule to deliver its protein cargo.
A pair of organelles called centrioles are located by or in the centrosome. Centrioles are short, barrel-shaped rings with 9 microtubule triplets forming their outer edge. As a cell prepares to divide, the centrioles are duplicated, and one pair moves to each daughter cell. In cells that have structures called cilia and flagella, the centrioles multiply and move to the surface of the cell, where they become anchored just beneath the plasma membrane, forming basal bodies. 10 pairs of microtubules grow out of each basal body. One pair grows from the center of the basal body, while the other 9 pairs form the outer infrastructure of a cilia or flagellum. A gap the width of a microtubule exists between each of the outer microtubule pairs. Numerous motor proteins firmly attached to one pair of microtubules have legs that cross the gap and can walk on the adjacent microtubule pair. The force applied by the motor proteins causes the microtubules to bend. The synchronized movement of large columns of motor proteins attached to microtubule pairs trying to walk up or down adjacent pairs creates the rowing motion of cilia and the wave-like motion of flagellum. Cilia, Latin for eyelash, are short and numerous structures that extend from the cell membrane. Cilia move single-celled organisms such as paramecium through their environment with a rowing motion. Flagella, meaning whip in Latin, are usually considerably longer than cilia and fewer in number. Flagella move in a wave or whip-like motion. The sperm of most animals and algae rely on flagella for movement, as do a number of single-celled organisms such as euglenoids. Microtubules are also believed to be involved with the movement of organelles, such as vesicles, within the cytoplasm.